Hello students, welcome back to another session of engineering chemistry, molecular orbital energy diagrams. So let us see the key points from the earlier session. So in the molecular orbital theory, we have seen that atomic orbitals combine to produce same number of molecular orbitals. The atomic orbitals that are going to combine must have the proper symmetry and energy to interact and forms the molecular orbitals. As the overlap between two atomic orbitals increases, the difference in energy between the resulting bonding and antibonding molecular orbitals increases. When two atomic orbitals combine to form a pair of molecular orbitals, the bonding molecular orbital will get stabilized about as much as the antibonding molecular orbital is destabilized. The interaction between the atomic orbitals is greatest when they have same energy. LCAO-MO theory, that is the linear combination of atomic orbitals, molecular orbital theory. It is a simple method for predicting the electronic structure of molecules. Now students, it is the time for reflection spot. Just answer to this question. State Aufbau principle, Pauli's exclusion principle and Hund's rule. Already we have discussed in the previous session molecular orbital theory. The filling of electrons in the molecular orbitals follows these three principles: Aufbau principle, Pauli's exclusion principle and Hund's rule. So as the molecular orbitals are arranged in the increasing order of their energy, the electron filling also takes place in the increasing order of their energy according to Aufbau principle. Pauli's exclusion principle, which states no two electrons in the same orbital will have the same set of all the four quantum numbers. And the filling of electrons also follows the Hund's rule of maximum multiplicity, which states that if there are any degenerate orbitals, the pairing of electrons in these degenerate orbitals takes place only once they are half filled. Now let us see the molecular energy level diagrams of homonuclear diatomic molecules. The relative energies of all the molecular orbitals are in the increasing order, as we have seen already. But in some molecules the order is having a slight variation. So here we can see the order from hydrogen. It is sigma 1s, sigma 1s star, sigma 2s, sigma star 2s, pi 2px, pi 2py, sigma 2pz, pi star 2px equal to pi star 2py and sigma star 2pz. Whereas for the atoms from oxygen to neon, there is a slight variation. The sigma 2pz orbital is somewhat having less energy here than in the previous case. As 2s atomic orbitals are of high energy, sigma 2s and sigma star 2s possess high energies than sigma 1s and sigma star 1s, which are formed from lower energy 1s atomic orbitals. Within the same pair of molecular orbitals, the anti-bonding molecular orbitals has higher energy than the bonding molecular orbitals. And the molecular orbitals of these two pairs are degenerate. So here it is given pi 2px equal to pi 2py and pi star 2px equal to pi star 2py. These are the degenerate orbitals. Then why the order of energy levels of sigma 2pz and pi 2px pi 2py is reversed in case of oxygen, fluorine and neon? So let us see the reason for that. In elements of lower effective nuclear charge, the energy difference between the 2s and 2p is least. So these two orbitals are very closer to each other. Because of that, there will be repulsive interactions between sigma 2s, sigma 2p, and between sigma star 2s and sigma star 2p. As a result, this leads to the stabilization of sigma 2s, sigma 2p, and destabilization of sigma star 2s and sigma star 2p. So this is the reason why there is a slight variation of the order of molecular orbitals. So let us see the molecular orbital energy level diagram in few examples. The first one, let us see in the case of oxygen. So as you know, the atomic number of oxygen is 8 and its electronic configuration is 1s2, 2s2, 2p4. And the oxygen molecule, that's why having 16 electrons. The ground electronic configuration of oxygen molecule is given here as already discussed in the earlier slide. So based on this configuration, these 16 electrons will get filled in these molecular orbitals. So as you are seeing in the picture, all the molecular orbitals are filled with the electrons following the Aufbau, Pauli's and Hund's rule. So finally, these two antibonding molecular orbitals, the pi star 2px and pi star 2pi, are left with single electrons. So because of this reason, oxygen is paramagnetic in nature because two unpaired electrons are there, and the bond order also can be determined from the formula half into Nb minus Na. So there are 10 bonding electrons on the whole and 6 anti-bonding electrons, so which gives the bond order as 2, which justifies the presence of two double bonds in oxygen molecule. So in this way, the molecular orbital energy level diagrams can be drawn, which predicts the bond order and also magnetic behavior of the molecule. Now let us see one more example, nitrogen. As you know, the atomic number of nitrogen is 7. The electronic configuration of nitrogen atom is 1s2, 2s2, 2p3. So a molecule of nitrogen has a total of 14 electrons, and the electronic configuration of nitrogen molecule is given here in accordance with molecular orbital theory. And these 14 electrons will get filled in the molecular orbitals based on the Aufbau, Pauli's and Hund's rule of maximum multiplicity. So after filling the electrons, you can observe there are no unpaired electrons at all. So the nitrogen molecule is diamagnetic in nature. And the bond order is obtained as 3 because there are 10 bonding electrons and 4 of anti-bonding electrons. So the bond order of 3 justifies the presence of triple bond in nitrogen molecule. Dear students, hope all of you followed the concept. So see you in the next session. Thank you.